Are we live, Rakesh?
Yes.
Okay, great. Hello, everyone. Welcome to another lecture of PNS Modern SSDs. In today's meeting, we are going to discuss how to enable fairness and high performance I/O scheduling in SSDs. And to this end, we are going to cover one of our paper in ISCA 2018 named the FLIN, Enabling Fairness and Enhancing Performance in Modern NVMe Solid-State Drives. So let's have a quick look at the executive summary of this work. Modern solid-state drives use new storage protocols, such as NVMe, that eliminate the OS software stack. I/O requests are now scheduled inside SSDs, which enables high throughput, millions of IOs. However, OS software stack elimination, it also removes existing fairness mechanisms. We experimentally characterized fairness on 4 real state-of-the-art SSDs, and we observed that highly unfair slowdowns, large difference across concurrently running applications. We find and analyze 4 sources of inter-application interference that lead to a slowdown in state-of-the-art SSDs. And to this end, to solve this problem, we propose FLIN, a new I/O request scheduler for modern SSDs designed to provide both fairness and high performance. FLIN mitigates all 4 sources of inter-application interference, and it can be implemented fully in the SSD controller firmware that uses less than 0.06% of DRAM space. Our experimental results show that FLIN improves fairness by 70% and performance by 47% compared to the state-of-the-art I/O schedule. Let's have a quick background on modern SSD design. So in modern SSD design, we have backend and frontend. So backend is to store data that we have memory chips. That usually we have NAND flash memory or 3D exploit in Optane SSDs. In some researchers, people also consider PCM. But yeah, basically in backend, we have memory chips. In frontend, we have we are doing management and controls. Logic, which is to implement the protocol used to communicate with the host. We have flash translation layer, FTL, that manages resources, processes I/O requests, and many other stuff that FTL is doing, like scheduling, word leveling, and also garbage collection that we covered in previous lectures. And we have also flash channel controllers, FCCs, that they send comments to flash chips to transfer data with memory chips in backend. So conventional host interface protocol for SSDs. SSDs initially adopted conventional host interface protocol, such as SATA, which is designed for magnetic hard disk drives. So in SATA, when we have different processes, for each process, we have an in-DRAM I/O request queue. And in OS software stack, there is an I/O scheduler that combines these I/O request queues in one queue and dispatches that queue to the SSD device. So the problem of this protocol is limited throughput. So the maximum of only 1,000 of IOPS per device is achievable. So this protocol, it was good enough for HDDs, but in SSDs, because since we can have much higher throughput, SATA can be one of the main bottlenecks. So in order to alleviate that problem, people introduced a new host interface protocol. So modern SSDs use high performance NVMe, non-volatile memory express as host interface protocols. So in NVMe, we bypass OS intervention, and SSD must perform scheduling. So Each process has a queue, and that queue can be directly communicated with SSD device. Excuse me. So the fairness mechanism that we already, we conventionally have in OS software stack now is also eliminated. So a good question is that, do modern SSD need to handle fairness control? So let's see if actually SSDs can provide good fairness or not. So in order to experiment on fairness, we did experiment on 4 real state-of-the-art SSDs. All of them use NVMe protocol, and they designed for the data centers. So we defined flow, a series of IO requests generated by an application. In order to calculate fairness, we first calculate slowdown for each flow. To this end, we first calculate the response time of that flow when it runs alone with no intervention of other flows. And we also calculate the response time of this flow when it is running shared among other flows. So by dividing the response time in shared scenario by response time in alone scenario, we can calculate the slowdown. So when we have several flows, each flow has a slowdown. So the maximum slowdown across these flows divided by the minimum slowdown we can calculate the unfairness, which clearly lower is better. And in order to calculate the fairness, we do basically we calculate the reverse of unfairness. Then higher is better. So to do an experiment, we did. Here we are reporting result for a representative example of 2 workloads, TPCC and TPCE. And so we can observe that basically TPCC has experienced some slowdown, but it's not comparable to the slowdown that TPCE experiences. So you can see that TPCE slowdown can be up to 600. And as a result, we have very low fairness. So this is the result for one example SSD that we tested. But overall average slowdown of TPCE across 4 real SSD that we tested is 2 times to 106 times. So we can observe that SSD do not provide fairness among concurrently running flows. So now a good question is, what causes this unfairness? So overall interference among concurrently running flows causes unfairness. But basically, what are the sources of these interferences? So we perform a detailed study of interference using MQC, detailed open source modern SSD simulator that we published in PASS 2018. In one of our past lectures, Rakesh provided a detailed overview of MQC. So if you are interested, you can also watch that lecture. So we run flows that are designed to demonstrate each source of interference. And we did a detailed experimental characterization result also in the paper, but here we are providing a summary of them. And we uncover 4 sources of interference among flows. So source 1, different IO intensities. The IO intensity of a flow affects the average queue wait time of flash transactions. So here as an example, we have a flow, synthetic flow, that we increase the flow IO intensity from low, like 16 megabyte per second, to high, 1024 megabyte per second. And we are showing the breakdown of the average flash transaction turnaround time. And in breakdown, we are reporting flash operation latency, bus transfer latency, and chip queue waiting. So we can observe that when we are increasing the flow IO intensity, basically the flash operation latency and bus transfer latency, they are almost unchanged, but chip queue waiting time is increasing. And at some point, it's the dominant factor that defines the total turnaround time. So the queue wait time highly increases with I/O intensity. As a result, when we are running the two workloads with two different I/O intensities, they can provide some interference. To evaluate that, we did an experiment to analyze this overhead, this scenario, and we have two flows with different I/O intensity. So we have base flow, which is has low intensity, 16 megabyte per second, and low, which as a result has low average chip level queue lengths. And we have interfering flow that we vary I/O intensities from low to very high. So here in this figure, we plot the slowdown for the base flow and interfering flow, and also the curves. So we can observe that when we increase the intensity of the interfering flow, the slowdown of the interfering flow is almost unchanged. However, base flow experiences higher and higher slowdown, which as a result, the fairness degrades drastically when we are increasing the intensity of the interfering flow. So we conclude that the average response time of a low intensity flow substantially increases due to interference from a high intensity flow. Another source is different access patterns. Some flows take advantage of chip level parallelies in backend. So consider that we have a blue flow that has wants to read 4 pages, and this flow can take advantage of chip level parallels. So all of these 4-page transaction can go to different chips. So we have chip level parallels, even distribution of transaction in chip level queues. So as a result, it leads to low queue wait time and high performance. However, this is not the case for other flows. So we can have some other flows that they have access pattern that do not exploit parallels. So consider a red flow that's basically 3 of transactions they are accessing chip 0, and one of them is accessing chip 2. So clearly, this red flow cannot effectively utilize the parallels in SSDs. So the problem is that when our blue flow that take advantage of, ideally should take advantage of parallels, is coming after red flow, it needs to wait for the red flow. And since the red flow does not take advantage of parallels, then the latency and basically the advantage of the blue flow is also gone completely. So in order to elaborate more on this, we also did an experiment. So we have 2 flows, the base flow that we consider streaming access pattern that is friendly for parallels, and interfering flow that we mix streaming and random access pattern. We increase the randomness of the interfering flow from 0% to 100%, which means completely random. And we basically in these plots, we show the slowdown for base flow, interfering flow, and fairness. So we observe that when we increase the randomness of the interfering flow, the slowdown of the base flow is increasing significantly. And as a result, the fairness significantly degrades. So clearly show that flows with parallels friendly access pattern are susceptible to interference from flows whose access pattern do not exploit parallels. Another source is different read-write ratios. So state-of-the-art SSD I/O schedulers, usually they prioritize reads over writes. We also covered that. And it makes sense because reads are usually on the critical path. And so we want to, and they are much faster compared to write. And we want to prioritize it. However, at some point, you are delaying your writes a lot. And then you may have some unfairness for the workload that have a lot of writes. So we also, to elaborate that, we did an experiment. So we have 2 flows, base flow and interfering flow. For the base flow, we consider 4 write ratio. So 100 write in ratio in base flow means that this flow is completely has only writes, and 0% write in base flow means that this flow has only reads. And for the interfering flow, we increases the read ratio from 0% to 100%. So interestingly, we can observe that when flows have different read-write ratios, so top left of this figure and bottom right of this figure. So when flows have different read-write ratios, existing schedulers do not effectively provide curves. Another source is different garbage collection demands. NAND flash memory performs writes out of place, which is because due to the property of erase before program. And erases can only happen on an entire flash block, which has hundreds of flash pages. So pages, and when we are writing, a page out of place, we are marking the old copy of that page as invalid. So at some point, we are run out of free pages, and we need to invoke garbage collection to reclaim free pages. And garbage collection selects a block with mostly invalid pages, moves any remaining valid pages in that block to free pages that we have, and erase that block. So we covered in the previous lectures that GC, or garbage collection, has huge performance overhead. And there are many ways, different researches and ways that also in vendors that they are reducing the overhead of GC. For example, by doing a progressive GC, that we are basically doing GC in parallel with other handling other requests, or when we are doing GC in the background in idle time. There are different techniques to reduce the overhead. So the problem is that when some flow, they have GC demand. So those flows with a higher write intensity, they induce more garbage collection activities. So garbage collection may block user IO requests, which can happen actually, usually, and it primarily depends on the write intensity of the workload. So when we have two workloads and one of them has high GC demand, can basically interfere a lot with the second workload, which is not high GC demand. So we did an experiment with two 100% write flows with different intensities. So for the base flow, we have low intensity and moderate GC demand. And for the interfering flow, we considered that we have different write intensities from low GC to high GC. And we evaluate 3 cases. One is that we have no GC, that we ideally consider that our SSD is large enough that we don't need garbage collection at all. And the default garbage collection, which is, this, let's say, greedy garbage collection implementation that we basically detect the block with highest number of invalid pages and copy those valid pages and erase that block. And a state-of-the-art work, SPGC, which is basically do preempt GC. So whenever we have some active request for read or write request, we can preempt GC in order to quickly service those requests and then continue the rest of GC operation. So we can observe that we have much lower performance due to GC execution. So when we increase the intensity of the interfering flow, that flow becomes high GC demand and interferes a lot with our base flow, which is low GC, moderate GC demand. and we can observe low fairness. So the GC activities of a high GC flow can unfairly block fresh transactions of a low GC flow. Okay. So to sum up, we have 4 major sources of unfairness in modern SSDs: different IO intensities, different request access patterns, different issues, and different garbage collection demands. Our goal is to design an IO request scheduler for SSDs that provides fairness among flows by mitigating all 4 sources of interference and maximizes performance and throughput. Okay, let's now have a very quick look at FLIN, our proposal. FLIN, flash level interference aware scheduler. So FLIN is a 3-stage IO request scheduler that replaces existing transaction scheduling unit. And it takes in-flash transactions, reorders them, and sends them to flash channel. It has identical throughput to state-of-the-art schedulers. And it can be fully implemented in SSD controller firmware, which means that it has no hardware modification, and it requires, our experimental results shows that it requires less than 0.06% of DRAM available within the SSD. So let's have a very quick look at 3 stages of FLIN. So basically, the goal of stage 1 is to handle different IO intensities and access pattern interference. So in stage 1, we do fairness-aware queue insertion. So consider that we have a queue request. So the head of queue we reserve for requests with low intensity, and the tail of this queue is reserved for high intensity flows, as you can see also here. So whenever we have a new request, if it belongs to low intensity flows, we basically move this request to the head of the queue and insert that there in order to make sure that this flow is not slowed down a lot due to the high intensity flow. And if it belongs to the high intensity, we basically insert it in the tail of that flow, tail of that queue. However, it's not the whole thing. So in that category, low intensity flows or high intensity flows, we also need to understand that which position results the best. So in order to do that, we also estimate the slowdown of that request, and we may need to reorder that transaction inside the category, low intensity category or high intensity category as well. So here as an example, we are showing that basically we are reordering this new blue transaction in the middle of that queue. So in stage 2, we do priority-aware queue arbitration. So this is important to enforce priority levels that are assigned to each flow by the host. So in modern SSDs, the host can define different priorities for different flows. And to enable this property of NVMe, we have also different queues with different priority. And we basically do weighted round-robin arbitration across these flows, and we choose basically, we select from the head of that flow. So stage 2 is basically, the goal of stage 2 is to select one transaction from one of these priority queues and send it to stage 3. And in stage 3 is basically, the goal is to handle read-write ratio and garbage collection demand interference. So we do weight balancing transaction selection. So we basically, we calculate, estimate the slowdown of that request, and at some point we can issue read requests or prioritize read requests as much as possible, unless we observe that that write request is waiting a lot, and the slowdown of that write request is becoming higher than the read request. Then we need to issue that write request. So the detail of this implementation and these techniques is in the paper. And if you are interested, I suggest that you check our paper. But yeah, the goal, the overall idea is here. Okay, let's quickly also see the experimental evaluation results. So in order to evaluate our technique, we use NQC, and the protocol we implemented is NVMe 1.2 over PCI Express. And the user capacity that we consider is 480 gigabytes. The organization of the SSD, we have 8 channels and 2 planes per die. And we have 4,096 blocks per plane, 256 pages per block, and 8 kilobyte page size. I mean, nowadays page sizes are usually 16 kilobyte, but this paper, since it was for 2018, I mean, the configuration is a bit outdated. And we have basically 40 workloads, mixes of workloads containing 4 randomly selected storage traces. So we have several traces from real enterprise data center applications like UMass, Microsoft Production Enterprise. And what we did is that we basically randomly select 4 traces across all our traces and make a mix workload. Because FLIN, when we want to evaluate FLIN, we should have mixes of workloads. And then we basically classified our mixes as low interference to high interference mixes. So we can have basically different levels of intensity, 25%, 50%, 75%, and high interference in our mixes. So we consider also 2 baseline schedulers as the comparison point. One of them is a Sprinkler, which is a paper published in HPC 2014. This is state-of-the-art device-level high-performance scheduler. And in order to see how effective prior Fairness scheduler, as we mentioned, I mean, previously we had Fairness IO scheduling inside the OS. So in order to see how effective are they, we apply that Fairness technique without any change on top of Sprinkler. And in order, this can help that we observe that how important is the problem that we are solving. So yeah, so the paper that we consider is from 2015. So the OS level Fairness technique does not have direct information about the internal resources and mechanism of the SSD, which is actually one of the main advantages of doing IO scheduling inside SSD. So at OS level, it's quite hard to understand what's going on inside the SSD. But when you're doing scheduling inside the SSD, you can basically have direct information about the internal resources and the status of them. And as you can imagine, OS level Fairness technique cannot mitigate all 4 sources of interference. So here we are summarizing our results, but in the paper you can see the result for each mix. So fraction of high intensity traces in workloads that, as I mentioned, 25% to 100%. And you can see that FLIN improves Fairness over the baselines. For example, for 100% high intensity traces, we can observe that Sprinkler is basically the result is quite bad for the Fairness. But Sprinkler plus Fairness technique that previously proposed for OS level Fairness technique can provide some Fairness. but FLIN significantly improves fairness compared to them. So overall, FLIN improves fairness by an average of 70% by mitigating all four major sources of interference. And here we are showing performance results. Again, we can see that FLIN improved performance compared to a sprinkler and a sprinkler plus fairness by 47%, which by making use of idle resources in the SSD and improving the performance of low interference flows. The main reason that FLIN provides better performance is, so sometimes we have some idle resources due to bad scheduling. And since FLIN scheduling is quite smart, intelligent, and do reordering, so ideally you can better utilize your resources in SSD, and it can improve the performance of low interference flow. So, and that's the main reason of performance improvement in FLIN. Okay. We have many other results in the paper. We have fairness and weighted speed up for each workload. We also have analyzed the maximum slowdown. So sprinkler and sprinkler plus fairness, several applications with maximum slowdown over 500 times. But using FLIN, we observed that there is no flow with the maximum slowdown over 80 times. And also, effect of each stage of FLIN. Remember that FLIN has 3 stages. So we show the effect of each stage of FLIN on fairness and performance, which is quite interesting to take a look. Overall, we observed that the first stage of FLIN is very important. Has more contribution on improving fairness. However, the third stage of FLIN is really important in order to reduce the maximum slowdown, because usually maximum slowdown happens due to the garbage collection, and when you are doing handling garbage collection interference, we can significantly reduce maximum slowdown. And we also did a sensitivity study to FLIN and SSD parameters and effect of write caching, which is also important. So I really encourage you that take a look at our paper to see more results, and also the detail of our technique. So to conclude, modern solid-state drives use new storage protocols, such as NVMe, that eliminates the OS software stack, that enables high throughput with millions of IOPS, which is crucial when we are using SSDs. So, however, as a, let's say, kind of downside, the OS software stack elimination also removes existing fairness mechanisms. And as a result, we have highly unfair slowdowns on real state-of-the-art SSDs. However, this also provides a very good opportunity, as we observe, since when we want to do a fair scheduling inside the storage, you have better understanding of what's going on and the status of your internal resources. And as a result, you can provide much, much better fairness compared to OS level technique that we have in the past. So we propose FLIN, a new I/O request scheduler for modern SSD designed to provide both fairness and high performance. FLIN mitigates all 4 sources of inter-application interference, different I/O intensities, different request access patterns, different read-write ratios, different garbage collection demands. And we show that our technique can be implemented fully in the SSD controller firmware that uses 0.06% of DRAM space in order to basically store those queues. And FLIN improves fairness by 70% and performance by 47% compared to state-of-the-art I/O scheduler, sprinkler plus fairness. And with that, I think I'm concluding today's session, but I'd like to wait for the 1 or 2 minutes to see if there's a question. Rakesh, do we have any questions?
No, no.
Okay. Okay, then, thanks a lot for joining, and we wish you a nice week, and see you all next week in our another lecture. In the next lecture, we are going to discuss reliability issues of SSDs and some of reliability issues and some potential solutions to reliability issues of flash and SSDs. So please stay tuned for the next lecture. Thank you, everyone, and bye.